Let's welcome Dr. Saad for today's lecture.
Yes, thank you so much for the invitation, and I appreciate that we had changes and the timing were accommodated. So in today's talk, I'm going to discuss some of our recent work on quantum communication. I'll also touch a little bit on quantum machine learning at the end, but not it's not the focus of this talk. Hopefully, a future talk I'll talk more about that. So we have been looking at quantum communication networks from the perspective of scalability, and I'll tell you later what I mean by that. Right? So scalability can mean many things, but I'll tell you what we actually mean by it. So yeah, the agenda of the talk, I'll do a couple of motivation. I know that this audience may not need it, but just in case there's just a couple of slides. And then I'll talk about the scalability challenges, right? What do we mean by scalability and what are the contributions there that we are looking for? And then the two main, if you wish, the core of the work will be in these two areas. So the scaling limits of quantum communication networks and the use of what we call reconfigurable intelligent surface for improving basically geographical distance or scalability of wireless based quantum communication networks. And I'll do a brief overview on quantum learning and some conclusions. So next generation communication networks must support a lot of increasing highly or data-hungry applications like the metaverse, like digital twins and extended reality. Now, of course, we have been doing significant advances in the classical communication community to meet some of those demands, and I think we'll be doing a good job there, right? So we will be able to do so. But if we try to think a little bit more like forward, it seems to me that there are other challenges that may emerge in terms of like the need for higher faster computing, the need for more data rate, and the need, of course, for better security, which with Moore's law and the starting to be violated, we can no longer stay in the classical domain. Quantum communication networks become more and more needed, right? I mean, I don't want to say reality yet because we know we're still at early stages, but quantum communication is essential. Of course, quantum computing in the broader sense, right? It's going to have applications beyond communication networks and so on. So in quantum communications, I mean, before I start a little bit, of course, I will use some terminologies that I'm sure, again, most of you know them, but just to be kind of complete, I will, of course, talk a lot about qubits, right? And as you know, a qubit is a superposition of a 0 and 1. And to obtain the information from a qubit, we have to do measurements, which end up collapsing the qubit and I mean receiving or extracting the information. We'll talk quite a bit on entangled qubits because we're primarily looking at quantum networks that rely on entanglement or teleportation, if you wish. So two qubits in no matter how geographically separated they are, would become correlated if they are entangled, and measuring one directly affects the other. So we use Bell states, as you know, to represent those and to do the measurements. And I'll talk about like in terms of performance, how good is my qubit, right? Is it good for communication? We're going to talk about the coherence and fidelity. So these are really the losses due to the interactions between the quantum or the qubits and the quantum environment, or even the classical environment if we're sending over a classical channel. So it's important for us to look at the coherence and to look at fidelity. So how good is my quantum state when I'm eventually going to measure? So quantum communication networks have multiple elements. One is the basically generation of qubits that happens in sources like NV centers and diamonds, or down converted laser beams. We do look, I mean, in a recent work, I didn't have time to include it in this talk. We do look at this issue of NV centers and how that affect communication, but not in this talk. And of course, the quantum channels are either fiber optics, so they're wired channels, and that's the most typical, at least for today. But we can also look at communication channels that are wireless, which is a free space optic, and I'll talk more about those later today. Of course, communication requires computing. So if just a brief insight on that, even in the classical domain, when we talk about 6G and beyond, we are now thinking on how do we use computing, classical computing, in the sense of machine learning or local computing, in order to to reduce the amount of information we need to send over a communication channel. So the need for computing is important, and that with that comes the need for memory and storage, right? So quantum memory is an important element of a quantum communication network, just like memory is an important element of future wireless networks. Of course, repeaters are also an important part in quantum communication networks. So quantum repeaters, I mean, if you look at the literature in quantum communication networks, the first when people started to work on that area, they really focused a lot on repeaters, right? Because they are important to allow us to basically extend the coverage. And I'll talk about repeaters later today. Of course, you can also have quantum switches, which allow routing, path selection, association, and the allocation of qubits. I'll talk a little bit on that as well, but the focus will be on initially a repeaters-based model, and second on the use of FSO with quantum. So scalability, right? Well, what does it mean? So of course, many people have different definitions, and you may disagree with mine, but at the end of the day, I have to give you some basis on what I call to be scalability. Of course, we want to scale the quantum communication network to become eventually what people call the quantum internet, because the quantum internet will have applications in QKD, distributed computing, sensing, and others. So what is scalability? For us, at least now, we're looking at scalability in the sense of extending the geographical length. So can I cover a larger area with quantum repeaters or quantum networks? Can I also scale the way I use resources, right? So memories, entangled qubits, can I use more of those? How can I make use of more of those? And of course, increasing the number of qubits that I can basically leverage on the network and computing power. So across these 5 elements that I mentioned earlier, so we're gonna look first at scaling quantum repeater networks. So if I have an optical fiber, just a wired communication network, and I want to go from a source to a destination, how long physically, like from a distance perspective, how long can my network be from the source to the destination? So how many repeaters do I need to place? Where do I need to place them? And how long can this be? And when we go to FSO channels, so when we're doing quantum over FSO, you start to deal with some of the wireless issues that we deal with in FSO or in the general wireless communication, like blockage. So the signal could be blocked. Now, you say, well, I'm a quantum network. I think even in wireless, we have this saying that I don't like a lot, but people use it when they want to kind of dismiss something. And they say, oh, well, the wireless network is a bit pipe. Why do I care? Well, here you would care because the performance of this bit pipe will affect whether your quantum communication is effective or not, right? So there's a coupling between how bad the channel is and how good is your quantum network. And that, of course, from a scalability perspective, also affects the distance, right? So how far can I go with this FSO channel? So the presence of non-line of sight links means that we need a different way to do it, or a different way to scale networks over geographical areas. That comes also in terms when I talk about distributed quantum computing or distributed quantum learning, right? How do I do that across geographically dispersed clients and a server in the sense of a federated model? So in this talk, the focus will be on the first two, so the yellow and the green here, right? So for the yellow, scaling QRNs over fiber, there has been work, right? I already mentioned that this is perhaps the most studied areas, but surprisingly, no one looked at scalability from a really kind of comprehensive perspective. There are works that look at scheduling distillation, but they don't look at really the lengths and the repeater placement. There are works that look at repeater placement. So I mentioned one by Da Silva here, but there are many others. But they usually ignore distillation and swapping and some of the quantum operations. And there are some QRN papers who are really looking at routing and really just QoS. Of course, here I list like 4 papers. These are representatives. There are hundreds of papers in this area. Our contribution is we're going to optimize jointly the length, the repeater placement, and the distillation operations in the presence of swapping, but we're not doing optimization to the swapping operations under various quality of service constraints. By quality of service, I mean 2 things here. One is the fidelity of the qubits, and 2 is the distribution, the entanglement distribution rate, or the entanglement generation rate, sorry, the EGR. So over FSO channels, when the channel is blocked, right? I mean, there has been a lot of works, usually assuming there's no blockage, because FSO in some cases, especially if you're not doing a lot of, if it's used in like these applications that are really very, very fixed, it could be line of sight, right? But that's not sufficient if you want to scale networks to a real quantum internet. So if there's no line of sight, there is one paper, and also to be a little bit precise there, that paper appeared where I mean, like the week before we submitted our paper, but there is a considerable difference between the two. So this paper said, well, we can use RIS, reconfigurable surfaces, and I'll tell you later what those mean, to basically overcome the blockage. The paper is interesting, but unfortunately, they don't consider the environmental losses. And even though they say quantum, they don't really consider the quantum aspect. So there's no entanglement generation rate there. There's no quantum noise effects analyzed. So it's an interesting point-to-point FSO problem with some quantum relevance, but it's not really what we want. So the contribution that we have there is that we look at the multi-user, not just a single link, with the presence of blockages, of course, and we're going to model the noise, the quantum noise and losses as function of the FSO channel. And then we look at how do you place the RIS and how do you improve like the EGR and other quality of service requirements. So let me start with the first work. So this work appears in the Quantum Computing and Engineering Conference, and we got the Best Paper Award in the networking track, the second place Best Paper Award. They ranked the Best Paper Awards in QCE. And this paper, we are looking at its extension now, and there's a lot of potential for it. But I'm going to start with just the conference version. So quantum repeater networks, as I mentioned, you have a source node and the destination node, and you're trying to basically send information over a quantum channel. There's, of course, noise and imperfections that limit scalability. You cannot do it across, an unlimited geographical area. Just like, and again, if there are some of you in the audience who are more in classical communication, just like interference and other metrics and other factors stop us from creating a cellular network over like hundreds or thousands of kilometers, we have similar limitations here. So we need to perform operations at the repeaters, and two main ones being swapping and distillation, and I'll talk about them later. So with that said, the end-to-end links are typically modeled as linear repeater chains. And the question is, how far can we go, right? What are the number of repeaters? What is the distance between each two, and how do we schedule their operation, specifically distillation, and what is the impact in terms of EGR, entanglement generation rate, and fidelity? So entanglement swapping allows us to extend the communication distance, right? So we're gonna allow our repeaters to swap. And at the link level, so when you see me saying link level LLE, that's what we call link level entangled state. It's just an abbreviation we use. So let's say you have two end nodes, and you each has a photon, and you have a quantum repeater in the middle. The quantum repeater can swap and create an end-to-end link between these two. So the FL and so on, these are the LLE states. Let's assume they have same fidelity. It's a reasonable assumption for now. And we're going to do a Bell state measurement. So using Bell state measurements and a swapping operation, we can create between these two end nodes an end-to-end state, which we call its function of FL, of course. So at the LLE level, if you have n-1 repeaters, I can do n-1 swaps, okay, to create to basically swap these photons and create end-to-end links. So you can see it at the bottom here. That here we're doing like we do some swap operations, and we do others on top of them, and we do others, and then we have an end-to-end link. So the question is, what happens to my fidelity? So fidelity will be affected, and after performing n-1 swaps, we can actually find the fidelity as function of FL and the number of swaps. So this is FL1 means I did one swap. Here I have FL, and N means I did N swaps. And then we have an expression for the fidelity. It's function of the 2-qubit gate fidelity and of a measurement fidelity of the entanglement swapping. And of course, it's a function of N, the number of swaps that we have done. So to enhance entanglement quality, we can also do distillation, and that has been in many works ignored or somewhat modeled in a smaller or modeled with less modeled with less precision, if you want. So every one distillation round, you can basically improve fidelity. At the expense, you can see we use photons. We lose photons. So we lose entanglement generation rate. So there's a certain basically a certain loss that occurs when you do a distillation. So you can see a trade-off coming up here, right? So once you distill 2 qubits in this case, you improve fidelity, and you lose in terms of entanglement generation rate. Now we have an expression for the output fidelity. This is not something we derived, so this comes from another very famous paper that does distillation. So it's function of the initial fidelity, of the measurement fidelity at that I had before, the 2 qubit gate. And the others are just constants that are well defined. So we can find the distillation probability of success due to imperfections as PS function of this F input, the minimum fidelity, which could be often is 0.5. So distillation has to be done n times. So when you repeat it n small n times, then you get a recursive function. Right, so we have a recursive function that gives me the fidelity. So the more you do distillation, the better the fidelity is. But of course, you can do it. You cannot do it in an infinite number of times, because then you lose a lot of photons. So again, these expressions on this particular slide, they come from others. We did not derive those. So the system model for us, we have a quantum source and a destination, and you have several repeater nodes in the middle. There's a distance d between them. We're going to assume d to be equal. In the journal extension that we're working on now, we are relaxing that assumption. It makes things more complicated, but we're going to see where to get there. But for now, we assume d is equal. And it's a linear chain. We have these link level entangled states between the, and we're going to do deterministic swaps. And we're going to do distillation only at the link level and end-to-end level. We're not going to do it multiple times, just for tractability. As you can see, the recursive function is very hard to deal with. So we have the swapping, we have the distillation and E rounds, again, at link level and at the end-to-end. And the quantum source, of course, here it has multiple qubits that are transmitted. So the question for us is, what is the maximum length of this quantum repeated network chain for given QoS requirements in terms, again, of entanglement generation rate and fidelity. And we can pose the problem, as you will see later, as an optimization problem. So just some assumptions. The LLE states are homogeneous Werner states with the same initial fidelity and the same initial entanglement rate. Neighboring nodes will do an L entanglement distillation followed by N swaps. Then we do this end-to-end, as I mentioned, the NE end-to-end distillation rounds, and we can find the end-to-end fidelity in this case. It's, again, the equation is based on the one I showed before, the recursive one, and then we can also find the end-to-end rate, which we need to constrain as function of the separation distance and of the fidelity of each end-to-end distillation round and the probability of success that I showed you before. So we can pose the optimization problem. We need to maximize this n times d. Again, the fact that we assume n equal d helps us in actually, I mean, it helps us in better modeling this. I mean, in better posing optimization problem, because when d is not equal, things become more complicated. But we are working on it. So we're trying to find the number of repeaters, the distance between them, the number of distillation you do at link level, and the number of distillation you do at the end-to-end level. And I mentioned quality of service many times. I need to guarantee a minimum entanglement generation rate, a minimum fidelity, and these are just, I mean, these constraints are just feasibility constraints. So they're not, they're just simple things. Like, you know, NL has to be positive, a number of repeaters, we need to have more than one. Otherwise, it makes no sense. And D is positive as well. The distance has to be positive. So the maximum length of the linear QRN essentially is what we're trying to find to satisfy these quality of service requirements. And these constraints, they appear because of you know, the whole operations we do, the swapping and the distillation, and these are the control variables that I already mentioned, right? So it's a challenging optimization problem. It's a mixed integer nonlinear programming, so it doesn't have a lot of solutions. We cannot find the derivatives, so we use a meta-heuristic solution to solve it. Keep in mind, this is an optimization problem done at the design time. So the quantum operator is really designing the system, and it's really I mean, it can be done offline, right? So it can be done in an offline manner, and then therefore it does not really matter if you use a meta-heuristic or you solve it in any way. What I want to say is that it's just, you know, it is what it is, right? You know, we cannot create a scale or a computationally simple way to solve this. But on the other hand, we don't need to, because it's a design problem, right? It's a design problem. It doesn't have to happen in real time, so we can do it offline. So some simulation results. So here in the first figure, I show the minimum required end-to-end EGR versus the optimal separation distance. Of course, first, as we intuitively expect, if you impose a higher rate, the distance will be smaller. I mean, you have to put more repeaters closer to each other. And if the initial rate is higher as well, if the initial rate is higher, then that also has an impact on the separation. So these reduced when a larger separation increases, right? Because you need to put more values. And what's interesting here is that the optimal values for D are not infinitely large. So they're kind of relatively small, like we have 4 kilometers or 5 kilometers and so on. The impact of these imperfections, right? So here we show this 2-qubit gate fidelity P2 that appeared in my equations. We show the scalability n times D here, and we show the measurement fidelity eta. And you can see like very interesting things here. Like when the measurement imperfections are worse, right? There's a greater impact on scalability compared to the 2-qubit fidelity, right? So you can see that measure eta. I mean, from this figure, you can see eta, which is on the left-hand side, has a greater impact on the distance, on the scalability. And if you have an ideal case, right? I mean, that probably doesn't exist yet. But if you have an ideal case where there's no device imperfections at all, so the P2 is 1 and eta is 1, which is really here, then you can have up to 267 kilometer. You would use multiplexing, but it's up to 267 kilometer. It's an ideal case. It's nice to recover it, but it's of course not practical. And in the next figure, we show the impact of not doing distillation, right? So if N L is equal to 0, scalability is reduced significantly. So this link level distillation is important, right? Even though it loses a bit in rate, it is important. And the number of swaps in N are reduced. So we have, 50% less number of swaps, N, which is also the number of repeaters anyways, because they're equivalent. It drops by 50% when F0 is reduced by 4% for a minimum Fmin of 0.5. And on the right-hand side, we remove NE, and we see it's very difficult to achieve end-to-end fidelity in this case. In fact, end-to-end distillation is somewhat essential, and that's the main message here. Otherwise, the number of repeaters is very small, and we cannot scale anyway our networks very much. So you can see what's interesting here is that this fidelity distillation, they have significant impact on the design of these quantum repeaters. And surprisingly so, this impact has not been studied as extensively as other things, and this is where we place this contribution. So the conclusion here is that you need to do the link level distillation, you need to do end-to-end distillation, and scheduling of those operations is important. Now, what are we doing now with this work? There's a couple of things. One is we are relaxing the assumption of equal D, because while that is useful for mathematical analysis, in practice, you may have different distances. And two, we are trying to basically look at a more effective scheduling of the distillation operations. So next we move to basically scaling over free space optics, right? So free space quantum communication networks and the use of reconfigurable surfaces. So as I mentioned before, if you have a quantum source node and a destination node, optical fiber is not always easy to install, which is why wireless is very popular, right? I mean, in the classical world, we know that wireless, basically took over, right? We don't, most of us don't have any more landline phones, and we use just smartphones or wireless communication. So wired communication has become less attractive, and we expect eventually, of course, not in the early days, but eventually that would be the case for quantum. But wireless is susceptible to blockage and obstacles, even when you use FSO, because there's no line of sight. So one solution is to use reconfigurable surfaces. What is a reconfigurable surface? It's the idea that you can create usually either through what we call a phased array or metamaterial, a large surface with a lot of small antennas next to each other, and then you control those antennas in basically a passive way. Like the RIS doesn't generate any signal. It's just like a mirror. It reflects the signal, and it allows us basically to overcome obstacles. And you can control, what we call the phase shifts of the RIS, and those phase shifts really affect, how you would reflect the signal. So the RIS basically creates this red line, if you want, which we can call, for the purpose of discussion, a virtual link, because in reality the link is end-to-end here, but it's blocked, so we can create an alternative route for that link, which we can call virtual line of sight, basically. Sorry, not virtual link. So if you take in 3D space, let's say we have a quantum, QBS here stands for a quantum base station that is trying to distribute basically information to multiple users. So here I have user L1, Li, Ln, and I'll use later L to denote basically the position of those users in 3D space. And we have an FSO channel. If you have blockages, you can use RISs. And in this RIS, as I mentioned, you can use part of the RIS for each user, and then you control how this is basically reflected to user 1, the orange one, how the blue is reflected to user N, how the green is reflected to user I, and so on and so forth, right? And then we can overcome the blockage. Now, of course, the base station itself has certain entanglement generation rate, and it also is located at LS. And the question for us is, the simple question we first ask is, if I have a quantum network using FSO channels, where do I place this RIS? Right? What is the optimal location so that all the users maintain their end-to-end rates and the communication links are reliable? So to do that, we need to understand the FSO environmental effects, the channel. What affects the channel? So there are four factors that affect an FSO channel. One is atmospheric loss, which we will use HP to denote. This is because of scattering of light by atmospheric constituents, and it's weather dependent, right? And it scales exponentially with distance. Second, you have turbulence. Turbulence is very famous in FSO. It's because of temperature fluctuations, which leads to variations in the refractive index. And there's usually a metric called the rate of variance that is used to capture the distortion of the phase of your FSO signal because of turbulence. And then you have the pointing error, which is basically a misalignment, because in RIS, you need to point what, again, if you're not in the communication community, this is what we call beam forming or beam distribution. So you need to direct or point your beam towards a user. So there are pointing errors because this might not be perfectly aligned due to vibrations, to instability in how the RIS is or how the transmitter or the RIS is actually placed. So the end-to-end channel gain between the quantum base station and user I has these three, not four, effects, which is the atmospheric loss, the turbulence, and the pointing error. And there are some, constants as well. Eta is not the same eta used in the previous paper. Okay, it's not the same. It's a different paper. So here it's just a constant. So we have the RIS location, we have the reflection efficiency, and we have the receiver responsivity at eta. And we have, of course, HP, HA, and HG. They are all function of LR, which is the location, in this particular case, the location of the RIS, but they're really function of the location of your transmitter and receiver as well. So the end-to-end entanglement generation rate is essentially the initial rate multiplied by a probability of success. This probability of success depends on where you place your RIS. So you have an initial entanglement generation rate, which is controllable, and you have this probability of success over the FSO channel. So we need to find the probability of success, and I think this is one of our major analytical contributions in this work. We actually can derive it. It looks complicated, but it's not. I'll tell you in a minute how useful it is. So it's function essentially of the turbulence, it's function of the atmospheric loss, and it's function of the pointing error. Now, the rest are either constants or they're variations of these metrics. So in some sense, I have the probability of success as function of the quality of the channel, as simple as that. And so now when you have an entangled pair of qubits, we can distinguish between two: a matter qubit, which is stored in the quantum memory, and the flying qubit, which is the one that we send over the FSO. So the matter qubit has a depolarization noise, and we call it capital lambda here. It's function of the following metrics. It's function of a density matrix that comes from the state. It's function of this 1 minus p, and I'll tell you in a moment what p is. And it's function of the identity matrix. And of course, there's 1 minus 4p and 4p. And p is actually this probability, which is function of the coherence time and the storage time. The coherence time, the memory coherence time, and the storage time. Remember, this is the matter qubit. This storage time itself is function of the end-to-end distance, the speed of light, and a processing time. Okay, so we have this quantum depolarizing noise. It's function of all these metrics. And we have the phase damping quantum noise. It's function of another probability of P2. It's also function of rho as well, of the Pauli Z operator sigma Z, and as well of P2, which is essentially an error function of this rate of variance, right? So we have the flying qubit that is subject to this phase damping noise coming from the rate of variance from the turbulence of the channel, and we have the matter qubit function of those memory effects and the end-to-end distance and so on, right? So now we can, for each user, for an initial entangled state, we can find the noise. So we can find the matter qubit is stored in the quantum memory, So this is the depolarizing noise. And second, the flying qubit travels in the FSO with pointing errors and turbulence. So we can find the resulting end-to-end entangled state as function of those metrics. Why is this useful? Because now I have a connection directly between FSO channel quality and the quality of the qubit, right? Both matter qubit and flying qubit. So here we can show, I mean, it's not very hard. We can show that this lambda prime 00, so for the first indices, is essentially the fidelity if phi 00 is the desired state when we measure. So we can find those as function, again, of P2 and of the time. And I mean, all of the factors you see in this equations are the ones I explained before. So the proposition, while the theorem is essential for us to establish, I mean, I'm going back to it a little bit, is essential for us to establish the probability of success. This proposition is really the one that links quantum communication to FSO. Now, once again, we pose this RIS placement and EGR allocation as an optimization problem. So we're trying to find the initial R for every user, the location of the RIS to maximize the entanglement generation rate with memory capacity, entanglement rate constant, fairness index, and the end-to-end fidelity. So you can see here the coupling on the FSO and the quantum network. Again, the optimization problem itself is not very simple to solve. So we use a heuristic. I mean, if I remember well, we use simulating annealing. And then I can show you some results here. So first, the simulated annealing algorithm is within 6% of the optimal solution, and it's fast, so that's useful. It's 65% faster. And here we can show an example with 2 scenarios and 2 different weights. So you can see here I weighted every user differently because different users may have different quality of service. So you can see with W1, we have equal weights, and W2, we have different weights, with user 3 being the most important. And scenario 1 is in orange, and scenario 2 is in green. And you can see the users where they are in orange and where they are in green. So in the orange case for W2, you can see that there's a shift of the RIS position here. So that as to accommodate, in the green case, so as to accommodate as much as possible the different users. And the actual for W1, when it's equal, you can see that it's kind of in the middle. And when the weights are different, it shifts a little bit further. And for the scenario 2, you can see W1 is very close to basically the midpoint. And W2 is really very close to the users because now we have users with higher weights. So this is just an example for 3 users. You can do it for multiple users. Now we can show also the end-to-end rate versus for every user. You can see that the proposed framework really allows us to basically be more fair across the users, because if you use, for example, something like log rate maximizing, all the rate goes to user 1 because he has a better channel. And that's not what we want. We want like fairness. We want to allocate the rates equally across the users, and more or less. In other words, if you use rate maximizing, it tries to give a lot of information or a lot of allocation for user 2, and it ignores a lot users 1 and 3. You can see there's blue is very small here, the blue is very small here. Our proposed framework is very fair, right? So it allows enhanced fairness about 64%. And we can see, sorry, here, what happens if we compare with what we call a fidelity agnostic? So it doesn't know about fidelity, an algorithm that says fidelity doesn't matter. So remember, I referred to a paper early on, and I said that paper doesn't consider quantum effectively. That could be FA. And another one that is not also agnostic to fairness, not just fidelity. And you can see that the proposed framework does much better, both in terms of the end-to-end fidelity and for different use cases. So the second use case is under strong turbulence on the right-hand side. On the left-hand side, it's a moderate turbulence. And we do even better when the channel is bad. Because when the channel is bad, your fidelity is significantly impacted, and being fair to the users goes a long way. And finally, under different weather conditions, so for good weather, strong turbulence, rainy weather, what is the performance in terms of the rate? You can see that rain actually has the biggest impact on your performance, right? So rain, which is the blue curve in this case, it significantly affects the performance of your network. And other metrics like pointing error is the second, and turbulence is the third. With good weather, you would be in the red curve. So in summary, here we before I go to other research directions, I think wanted to convey the point here. RIS allows you to extend the coverage, so you create this virtual line of sight link, but you are still subject to strong turbulence, to rainy weather, to pointing errors, and those come from just the environment. So how do we account for those? We derive the dampening noise, and that helps significantly in that. So what are other things we've been doing, right? So there are other areas we've been looking at. We've been looking at scaling quantum memories, and basically I mentioned before, like how do we take into account more realistic cases for the repeater network. We have been also looking at delay-aware networks. So what if you want to take into account the delay across the memory and the scheduling? This work actually already appears on arXiv, so you can see it there, and it looks primarily at the delay in quantum communication networks. And we also look at scheduling these distillation networks, and at how we allocate jobs if you have a switch. And I'll show you a little bit on that. So this is a GlobeCom paper from last year. I'll be very brief on this one. Let's say you have multiple transmitters and multiple receivers, and there are a subset of quantum switches. And there are jobs, like computing jobs, I need to execute, and these need communication between the transmitter and receiver. The question is, how do I associate those with the switches and with the nodes? It's a very complex optimization problem, but we show that you can use techniques like matching theory to actually solve the problem and get an optimal association. You can see the F that I used a lot in these slides, so we have fidelity taken into account, of course, and this work. And we can show eventually that using this, what we call a request quantum switch association algorithm based on matching, it's much better than a greedy algorithm. It's very close to the optimal, which is the black one. And of course, it's much better than just randomly allocating your jobs in this use case. And we also looked, this is a little bit, this slide precedes the work I presented. So we were initially talking about how we can bring this physics from quantum physics, so real quantum metrics like the coherence, like probabilistic nature, into communication networks. And the message there was not only technical, it was saying, we need to collaborate with quantum physics community, because for communication, oftentimes we ignored all of these things, and we look more at like problems we are familiar with, like scheduling, for example. So this advocation for physics-informed controls and metrics, I would say, like the noise that we derived, for example, that's a physics-informed noise channel for FSO, and this leads to a lot of problems, a lot of open problems in signal design, scheduling, and distributed quantum computing. And federated learning, so there was initially some interest in this. I did not present it today. The idea of federated learning is that you can do quantum or you can do machine learning across multiple devices by only communicating model parameters. So you don't need to communicate everything. So the question for us was, can we do that with quantum neural networks? And can we do that with actually quantum data set, right? So if the data set is purely quantum, of course, this is simulated. We don't have sensors to collect real quantum data. But what we did in this paper, we had 3 contributions, I think, and they are mostly on implementation. First, we defined how quantum federated learning looks like, right? So it's of course follows the classical, but how do we distribute? What do we share? Like we share the quantum circuit parameters in this case. We developed a public quantum federated data set, so you can find the paper, and I think we have a link on GitHub for the data. How do we generate it? And we used, it was a really pure software work here, but there's a lot of challenges to do it, which is why we had to integrate for the first time TensorFlow federated and TensorFlow quantum, not Qualcomm, quantum within Google Circ and a new implementation. So we went a little bit further in that work recently, and we looked at how you look at quantum long short-term memory, so federated long short-term memory. So we have a collaborator who works at Wells Fargo, and he was the one to propose the idea of quantum LSTM, and we looked at a federated version of that. So we are really looking, if you think, what are you doing in quantum? We are trying to look at the in quantum federated learning. Sorry, we looked at the foundation, like, how do you design those? Whether the network is classical, whether it's quantum, what are open problems? If you're interested, so there's a QR code here. We have a magazine paper, which is really more about discussing the vision and the open problems there. So in conclusion, scaling quantum networks is an important problem. There's a lot of angles and dimensions to it. I only covered 2. We need fundamental analysis, right? So physics informed, basically taking into account real operations like swapping and distillation and how they impact the communication network performance. We can use optical, we can use FSO, and each has its own challenges. RIS is useful in FSO. I think our paper is an initial step. You can think of many other ways to use RIS there. Again, I want to say, the underlying physics. So as wireless classical communication folks, we need to speak more with quantum folks because we cannot really build networks by just repeating what we do in the classical case. And of course, this distributed computing, so we call it federated, but it's really distributed computing is another area of a lot of interest. It has communication, it has computing, and it has machine learning in it. And finally, I'll be happy to answer questions. And again, thanks for the talk and for the invitation.